For lesson 2.9, we are going to take our findings from our previous lesson on the slope of x squared and try to expand on the idea to figure out the derivatives of x squared's function group, which is power functions. So in our last lesson, we were able to figure out that if we took the slope between every integer value for x squared, we could figure out a pattern of slopes that when combined with an over and underestimation, we could get an average slope that would actually create a function for us. Simply put, we figured out that the derivative of x squared is 2x. We also had a couple of variations on this point. We only had an overestimate for one and an underestimate for the other, so we didn't really get the chance to average the two things out. But to just show what actually happens with that, the other side of the functions that you would have got here, for x squared minus 4, the overestimate function is 2x plus 1, and the underestimate function was 2x minus 1, just like the functions that we got for x squared. This means that the derivative averages out to 2x. And that lets us know that if you are adding or subtracting a number from x squared, the derivative stays the same. Having some number on the end doesn't seem to have any effect on the derivative at all. However, if you take both the over and underestimations for 3x squared, 6x plus 3, and 6x minus 3, those average to 12x over 2, which was 6x, meaning that putting a multiplier on x squared does seem to affect the derivative. At this point, the only thing that we kind of really know for certain is these three derivatives. We're not really sure of a pattern yet, which would be the thing that we want to figure out at this point. Now that we know that derivatives exist, we want to find as many of them as we can, because going through this process of looking for a pattern in a table, though effective, is arduous, and we could probably do something simpler. So the operative question that we have right now is, why is it that when we go from the original function to the derivative, x squared turns into 2x? What could be happening to this function to get it from here to there? Is there any sort of link at all? Well, there's a number of different algebraic operations you could do to technically turn this into 2x. But what if we had a little bit of a simpler thought here? Maybe instead of thinking of x squared as like a math term, what if we thought of this as like an image? In that sense, if we were able to manipulate this image, what would we need to do to it to make it go from x squared to 2x? Well, if you have a visual mind, you would probably say that it would make sense to take the 2 from the exponent and just move it down in front of the x. That seems to be what has happened here. Even in the situation with 3x squared, it would still kind of make sense if this 2 was moved down in front of this 3 if you just expected these two things to multiply together. So maybe all we need to do is just get rid of the exponent by like making it a coefficient in front of x, and then we will be able to get our derivative? Is that what's happening here? Let's test that theory. So here we have the function x cubed, and we want to try to figure out what the derivative of this is. Our current theory would lead us to believe that we can just take this exponent and move it down in front of the variable here, meaning that the derivative should be 3x. If x squared gives you 2x, x cubed should give you 3x. That seems like it makes the most sense, right? So here we have a table of values just like before, and a set of y values that we can actually just figure out on our own by cubing all of these things. 0 cubed is 0, 1 cubed is 1, 2 cubed is 2 times 2 times 2, which is 8. 3 times 3 times 3 is 27, and 3 4s multiplied together is actually 64. We get the same values on the negative side of this, but in contrast to x squared, x cubed is capable of getting negative values, meaning that this is going to be -1, -8, -27, and -64. We're going to do something a little bit different with these values in contrast to the previous lesson. Instead of taking the over and under estimations by taking a slope that's 1 away and then averaging the two results, we're just going to take the slope of each of these points with a really, really close by point. Basically just like 0.001 bigger than each of the things that we have here. Part of the reason that we have to do this factors into what the actual derivative of this equation is. But for now, let's take this process over to Desmos to see if we can get some points. So here's the same table of x and y values that we had on the assignment, and then this is what I was trying to explain with the slope. We're just going to take each of these points against a point that is just a little bit bigger than it. This does technically make all of these an overestimation, but we are so close to the actual point that it's probably going to be negligible in terms of how we need to round. And we can see pretty clearly what all of these points would be if we rounded them off. Here our slope would round to 48. This one would round to 27, to 12, 3. This means 1 times 10 to the negative 6 power, which means there's 5 decimal places or 5 zeros in front of this 1, so just a big 0. 3, 12, 27, and 48. So already we can tell that this is not a linear function because these are not negative, meaning that these are actually kind of all the same y values that are looping around this center point here. When we put these points on a graph and connect them, we can see that the derivative graph that we have here is a quadratic. This is the reason that we also weren't able to take an average of the over and under estimations to get an accurate view of what the derivative is, because the derivative isn't a linear function where averages work a lot better with a constant slope. We know now that this has a changing slope, so it wasn't going to work the same way. So already we know that our initial guess of 3x was wrong, but could we figure out the exact equation of the graph we're looking at here and then maybe tie these results together to actually come to a logical conclusion? Well, one thing I'm noticing from both the image of the graph on Desmos and also the fact that we have this 0, 0 point here means that our quadratic is centered at the origin, so there's no horizontal or vertical shifts to it. At most, there could be some sort of dilation, so this is of the form ax squared. Normally, when you just plot regular x squared, the y values that you would get out of it would be 0, 1, 4, 9, and 16. When I look at the derivative slopes that I have here in comparison to the normal points of x squared, I immediately notice that all of these are 3 times as large. So it would be logical to conclude that the derivative of x cubed is actually 3x squared. So we had the right idea with this exponent moving down in front, but the one thing that we weren't seeing was the power right here. How is this a detail that we missed when figuring out regular x squared? The big reason is that this x technically has an exponent of 1, something that we don't think about very often because when something has an exponent of 1, we don't have to list it. But when you actually put this up here, this whole situation not only makes more sense, but is a lot more consistent with what we have right here. We can now basically amend our idea of how to get the derivative of x squared into how to get the derivative of a power function in general. The process seems to be take this power that is down in front, multiply it by anything that might already be sitting here, and then drop this by 1 instead of getting rid of it entirely. This process can even be shown with a generalized formula where if f of x is a times x to the n, then the derivative is going to be a times n times x to the power of n minus 1. So bring the power down to multiply whatever is in front, and then drop the resulting power by 1. This is called the power rule, and it works to get the derivative of any type of function that's of this form, which is basically a power function. Even if you had a function that had multiple terms in this, like some sort of standard form quadratic or other polynomial, you can still get the derivative of that equation by just doing the power rule on every single term. This is an extremely powerful shortcut and is super cool. We figured out what the slope of a curve is. It's a function, and even some of them have like specific functions that follow patterns, meaning that like we just figured out the derivative for like 6 or 7 functions. We could get all kinds of slopes now. This is pretty amazing. Also, before I end this, I wanted to show the Desmos file in a little bit more detail here for 2.9. I've got this here where I typed in my given equation, which was x cubed. And then down here, I just typed in my x values from the table. This generated the y values, the really close by slopes, and then the rounded slopes here are coming from the fact that this is just automatically generating the derivative values for f of x. So if you were to change the function at the top, you could also get the values and see the pattern for any other type of power function here. All right, so that's really cool, and that's basically everything we have to talk about in Unit 2. Thanks for paying attention to all that. Slope of the curve, we did it. That's cool. We'll do some more math soon. Bye.